And, oh, that's not the screen. There's the screen. Hello, world. All right, here we go. So this is number 5, is that right? Mm-hmm. All right, so this is section 1.6, which is about exponents and logs. And this is number 5, and homework assignment. So a substitution is an educated guess and check process, and it's using the chain rule, which means we have inner functions to think about. So when I look at this up here, I see a couple of things. I see a quotient, which is a function. In the quotient, I see a logarithm. So a logarithm is a function within the quotient. And I see 8x, which is within the logarithm. So I have a function within a function within a function here. Okay. So my first guess at an inner function would be to let u equal 8x. The derivative, du, would be just 8 dx. And that doesn't get rid of much, because I'll still have a u here and a u here and some constants. Okay, so I'm no better off there. So my first guess at du wasn't good enough. And that happens, right? You don't always choose the right substitution. So what's the next thing I should try?
U equals ln 8x.
Yeah, use the ln next. So that's a function within a function. So next I let u equal natural log of 8x and see if that's more productive. What would du be?
With 8 over 8.
So first it'd be 1 over 8x, and then the chain rule says take the derivative of the interior, which is 8. So it would just be 1 over x dx.
No dx.
Okay. Now, cool thing here is I have a 1 over x sitting right there.
Cancels.
Okay. So my du in this case is here and there. So now I go in and start replacing stuff. All right, so let's see. The 5 I'm going to pull out. That's a constant. Integral 1 over dx, 1 over x dx. That's my du. I'm going to write that over there. So let's see. I'm taking care of that. The 1 over x to 5. Next is 1 over the natural log of u. And now I've accounted for all of the pieces.
No, wouldn't it be just 1 over u, because the
Oh, natural log is u. Yeah, u is natural log. Thank you. That's wrong. Stuck on the previous substitution, apparently. So yeah, 1 over u. There we go. That cleans up dramatically, right? All right, so then next thing I would do is rewrite that as u to the negative 1. And what's an antiderivative? Actually, I guess I didn't need to do that. Yeah, 1 over u antiderivative is natural log. So that wasn't necessary.
Why don't you just leave it there?
All right, so I get equals 5 times the natural log of u plus c, and then reverse substitutes back into that. So switching colors, I get 5 times the natural log of, what's u again?
The natural log of 8x.
Yeah, so I get the natural log of the natural log of 8x plus c.
Would it be absolute value?
It should be absolute value, right? Color, absolute value goes around the u, so out here is the absolute value.
I'm just having trouble typing in my computer.
Okay, so how would I type that in? Good question. Let's see, that was number 5 here. To enter absolute values, do not use bars, but use the function abs of x. Okay, so then that means I'm going to have the natural log, parentheses.
5 times.
Oh, 5 times, yep. 5 times the natural log, parentheses. I like to start and close my parentheses and then go in between them, so I know where they end. So then in there, I have the abs for absolute value, parentheses, parentheses. Inside the absolute value goes ln, parentheses, parentheses, and inside the ln goes 8x. And I also noticed that some of these ask for a plus c and some of them do not, which is, I got to fix that later.
That one is a plus c.
Yeah.
This one probably wants to
What do you
always.
need for the ABS? for the absolute value for 8x as well?
No,
Because U
technically,
is ln AX.
let's see.
And with the absolute
It
value.
doesn't-
I don't think so.
Because when you wrote it, you did it around the 8x, not the.
I did it around the whole thing here.
Okay.
Yeah, because technically, the antiderivative of 1 over u du is the natural log of the absolute value of u. So according to that rule, the absolute value should go around that whole u thing. Good question. All right, I think I typed that right. Submit. And I like the way I typed it. Yeah, so typing these in is a challenge. Sometimes it can help to use the editor up here. And then save it and it'll type it in. But use of parentheses is often a problem for me and everybody else. All right, moving on. Question about number 17. So same section, 1.6, number 17. All right, so here we have a function within a function. So the outer function is the fraction. The inner function, you could say, is either 3 plus e to the negative 8x or just e to the negative 8x. I'm going to try picking the whole denominator and see what happens. So first try u equals 3 plus e to the negative 8x du would be, the derivative of 3 is 0. Derivative of e to the negative 8x is e to the negative 8x times negative 8x. And problem.
You said D equals.
du. Miller. Problem is I don't see du sitting there. You? No. Okay. So that didn't work. Next, algebra. What does a negative exponent mean?
Put it in the negative.
It means flip it, right? So essentially, this function right here is 1 over 3 plus 1 over e to the positive 8x. So I have a fraction within a fraction. So I'm going to eliminate that. So to do that, I'm going to multiply top and bottom by e to the 8x. Okay, so that gives me e to the 8x over 3 e to the 8x plus 1. Right, because I get to distribute through here in the bottom. So this is another version of the function I'm trying to take the derivative of. Do you see a substitution might work now? Yeah. Okay, so what should I let u be here?
8x.
3 to e.
Let it be the whole denominator. That's my recommendation. So e to the, what is it? 3e to the 8x plus 1. So then du is going to end up being 8 times 3 is 24 e to the 8x dx. Okay, so I have everything but the 24.
So
Should I
if we just
do about that?
multiply it by 24,
You could, by what was that, 1/24th?
by what, yeah.
Yeah, so I'm just going to rewrite this and say that e to the 8x dx is 1/24th du. So I'm going to replace this with that. So new page, I think what I have now is I'm going to pull the 1/24th out of the integral, and I think I just have 1 over u du now. Right, double check. Here's my du. This is the only thing not accounted for, and that right there is really my u. Yeah. So there's 1/24th from here, 1 over u du. All right, antiderivative of 1 over u. Natural log of the absolute value, so I get 1/24th natural log absolute value of u plus c, and then we put u back in there. So actual answer, and let's switch to black, should be 1/24th natural log absolute value of 3 times e to the 8x plus 1 close absolute value plus c. And then the fun part about entering this into the computer, 24 natural log parentheses ABS parentheses, then your 3 times e raised, that's a power, to the 8x has to be in parentheses, then plus 1. Ooh. So lots of parentheses here, and then maybe a plus c.
It gives it a plus C, I think.
It gives the plus c there. Okay.
That is what you would type in.
Ooh, that was a workout. Nice. Everyone warmed up? Ben's invigorated. All right, moving along. We are going to go back and talk about some functions we've done before. This is section 1.7. I promised more transcendental functions. Transcendental function basically means it's not a polynomial, it's not a rational function, it's not a square root kind of thing. It's something like sine, cosine, e, log. So we're going to do inverse trig. So first, a lot of what we know about integration is based on antiderivatives, which means we need to know derivatives. So for example, the derivative with respect to x of, let's go with the arctan. Anybody remember what its derivative was? Almost? That's the sine or a cosine, arcsine or arccosine.
1 over x squared plus 1.
Yes. That's the derivative of the arctangent. The antiderivative of 1 over x squared plus 1 must be arctangent. So definite integral of 1 over x squared plus 1 dx is equal to the arctangent of x plus some constant. So I'm going to prove this or similar. Yeah, I guess I'll do this one in a different way than I did last time. Last time I used the inverse function theorem. Anybody remember implicit differentiation? That's what I'm going to use today. Okay, so here's the deal. Let's suppose that y is equal to the arctangent of x. I can rewrite that. Actually, we're going to do a more general case. I'm going to call that x over a 1. I can rewrite that by saying x over a has got to be the tangent of y. One more step solving for x, I get x equals a times the tangent of y. So one way to think about this is the if I just put an x and not an x over a, that's like having a radius of 1. If I throw an a in there, that gives me some like arbitrary radius. Okay, that's a way to think about it. Now, here I can use implicit differentiation. And implicit differentiation means you acknowledge that y is a function of x. So I have to use the chain rule. So I take the derivative of each side. The derivative with respect to x of x should be equal to the derivative with respect to x of a times the tangent of y. Left side's easy. What's the derivative on the left? 1. On the right, a is just a constant. It just tags along as a multiple, right? Constant multiples tag along. Derivative of tangent.
Secant
Squared.
secant squared. But the chain rule says y is a function you have to multiply by the inner function's derivative. Derivative of y, we could just call y prime, or dy dx if you like. Shrink this a little bit so I can fit all of this on one page. Almost done.
We don't have to use the product rule on that
I missed part of it.
right side.
No, because a is a constant. The product rule is not necessary. Here we go. Shift you up, shrink you just a little. All right. Next, solving for dy dx, I just have to divide the a secant squared y to the other side. So dy dx equals 1 over a times the secant squared of y. So now I just have to figure out, well, what the heck is the secant squared of y? Because I don't want a y to be in here. I want that to be in terms of x. To figure that out, I have to go back to this statement right here. Second from the top. Figure out what that means. Tangent in a right triangle is opposite over adjacent. Sorry, yeah, opposite over adjacent, right? So I'm going to draw a picture of that. So here I'm saying y is the angle inside, right? Because I'm taking tangent of y. So x is going to be the opposite side, and a here is going to be the adjacent side. What's the hypotenuse then? According to the Pythagorean Theorem.
X times. Wait,
X squared is x squared.
X squared plus a squared is going to be square root of all of that. Yeah. So Pythagorean Theorem says square the legs, add them up. That's this side squared, so this side must be the square root of that. So that's that side right there. Okay. So now that I have that up here, I can tell you what the secant of y is, or the sine of y, or any function of y. What is secant?
1 over cosine.
1 over cosine. So cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent.
But isn't it technically 1 over, like, in that function?
Okay, so secant is 1 over, is the reciprocal of cosine.
Can't we flip it though, because it's on the,
Oh yeah, we could call that cosine squared if we wanted.
okay.
Yeah, that would work too. Yeah. And we have to square it also. So secant, let's see. So this, we could call this, okay, I guess I can rewrite it. So this is a times, oh shit, it's in the wrong spot. This could be also viewed as the cosine squared of y over a. Cosine here would be adjacent over hypotenuse, so a over the square root. But then I'm squaring it, right?
So you don't have to put,
So that means I'm going to end up with an a squared in the top. And I'm running out of room. Okay. Slide you over a little. I have an a in the bottom, and then I have the square root squared, which is just x squared plus a squared. And that's going to clean up just a little bit. One of the a's cancels in the bottom with one of the a's in the top. So ultimately what I have here is that the derivative with respect to x of the arctangent of x over a is equal to a over x squared plus a squared. That's what it cleans up to be. So that tells me that the antiderivative of a over x squared plus a squared with respect to x is the arctangent of x over a plus some constant. And manipulating triangles like that is something that's going to come up again in the next chapter in terms of evaluating some integrals.
Didn't you get the a over x squared plus a squared?
So back here, I have an a in the bottom, that's this one right here. Okay. Cosine is adjacent divided by hypotenuse, so a over the square root, but I'm squaring the cosine.
Okay.
So that's going to give me an a squared over the square root squared, which is just x squared plus a squared.
Oh, so it's not the square root anymore?
No, because I'm squaring it.
Oh, I see.
Yeah, because I squared the cosine. Yeah. And then this a right here goes into one of those a's up there.
You go to the next slide, Dan.
So the result is that. All right, so we're going to do that same process again on the secant, and then we'll solve some problems with this.
Oh, is that why if you plug 1 into A, then it'd be 1 over x squared?
Yes, right. So I just did a general case of that.
Oh.
Right, with the one. Yep, you got it.
Makes sense.
Nice.
I
All
was like,
right.
I'm trying to worry about that. A,
So let's try that again. Let's see if your trick gets better. So we're going to let y equal the arcsecant of x over a. We're going to follow the same procedure we just followed.
Why are you doing all the hard ones?
Why am I doing the hard ones?
Yeah.
Because the easy ones are easy. So first thing I did before is I rewrote this as x over a equals the secant of y. Before we continue, let's draw a triangle that represents that second line. So the second line says y is an angle in a right triangle. Let's see, secant, let's see, is 1 over cosine, right? And cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So that means the hypotenuse here must be x and the adjacent side must be a. So Pythagorean theorem, if you call this side over here b, says a squared plus b squared equals x squared. You solve that for b, you'll get an x squared minus a squared over on the other side, and then you'll have to take the square root of that. And so that's your b right there. So that's going to be coming in handy after we do our implicit differentiation. All right, let's do our implicit differentiation. So to do that, I'm going to rewrite this one more time as x equals a times the secant of y. And we take the derivative with respect to x of each side here. What happens on the left? 1. A is a multiple, so I just go a times derivative of secant. Think.
Secant tangent.
Secant times tangent, so then I'm going to get a secant of y times the tangent of y. Chain rule says, do what next? Multiply by y prime. So if I solve for y prime, all this other stuff gets divided over. So y prime is going to be 1 over a times the secant of y times the tangent of y. Now we just have to look at the triangle, you okay?
Yeah.
Okay, and figure out what the secant of y is and the tangent of y is according to the equation. So secant is going to be hypotenuse over adjacent. So I'm going to have 1 over a times x over a. That's the secant. Tangent is opposite over adjacent. So that would be the value of b over the value of a. B is the square root of x squared minus a squared over a. So this right here is my secant of y according to that triangle. And this right here is my tangent of y according to the triangle. Cleans up dramatically. Millie, you look excited about this, you're right?
Yeah.
It's unusual to see you excited about this.
No,
Yeah. There's something else you're excited about?
whenever you go down there, you're like in a lunch. It just looks really stupid.
We'll talk. Okay. So, what do we get now?
The A's for X.
We get some cancellation of A here. So this one goes away, you could say. This A right here, I could flip to the top. Okay, so what we have then is the derivative with respect to x of the arc secant of x is equal, x over a, sorry, there we go, is a over x times the square root, the order x squared minus a squared, x squared minus a squared. So now we know that the antiderivative of a over x times the square root of x squared minus a squared dx is the arc secant of x over a.
Plus C.
Yep, you got it. So you have two choices now. You can memorize formulas like this, or you can remember that process when you get stuck.
That seems like a very long process.
I love that process. I think it's beautiful.
I mean,
But most of the time I remember the formulas. Not all the time, but most of the time. But this process is going to come in handy when we do some other problems later. They're going to allow us to solve some problems we wouldn't be able to solve otherwise. All right, so what do we have next? Test. Let's see if there's any cute homework problems first. So the only thing new there is that process, which is a little different than the way we did it last term. Oh, this is a cute one. Let's start off with this one. New page. Oxy. All right. This is number 1. All right, what does this look like?
arctangent?
Yep, except the arctangent the things were distributed a little bit different. So yeah, this is going to be related to the arctangent. Now the 49 presents a slight problem because that's not in the formula.
Basically, out.
Is this a multiple? So you can just shove it out?
It's a
Or is it
multiple only
one
of the
over
x squared, not of the whole thing, so I can't pull it out. Yeah, I'm stuck with it where it is. Okay, so think about 49. Why is that a special number?
7 squared.
It is 7 squared, yeah. So what I have here is the integral of 1 over 7x squared plus 1 dx. So one way to do this is do a U-substitution. Let u equal to 7x. So then your du would be 7 dx. So we're missing that 7.
So just 1 second.
If I add a 7 here, then I would have to compensate with a 1/7 outside. That's okay. That's a little different than I did it before, but that works. So now I have the u and the du, so my belief is that the answer here is 1/7 times the, oops, not the tangent, but the arctangent of 7x, because that's my u, and then plus c. How can I test that to see if it's right?
Take the derivative.
Take its derivative, yeah. So just to check this out, I'm going to take its derivative. So the 1/7 is a constant, it tags along. Derivative of the arctangent is 1 over whatever is inside of it squared, so that would be a 7x parentheses squared and then plus 1. And then the chain rule says multiply the derivative by the derivative of the inner function, which is 7, which cancels the 1/7, leaving me with the integrand I started with. So it does check. So I'm happy now. That's my answer. All right, not too bad. Substitutions are still helpful in envisioning the answer. All right, we'll do one more and then we'll take a look at the sample test. Let's see, 14, is that a cute one? 14 is very straightforward. 15 is not very straightforward. All right, let's try this one. New page. Oops, wrong button. Well, let me fix it.
What was that?
This is number 15.
Person.
All right, what does this look like?
Well, you have a dy, so it's.
Yeah, so I mean, we could rewrite it with a dx, so that's not a big deal. So if this was an x and that was an x, that would be okay. No,
Sine?
not secant.
Sine.
Sines, okay, so the sine, the formula, if you look it up, blue, the antiderivative of, let's see, how does this work? I think it's a over the square root of a squared minus x squared dx is equal to the arc sine of x over a is the general formula.
I think that's right.
90% sure that's correct. So let's see, what do we have here? Well, the a would be 5. Now I can see that from this right here. Because that should be the a squared. Now, I don't have an a up top, but I could easily throw one in and compensate for it. The 4, that's an interesting one here. That's a 4y squared instead of an x squared.
2y squared.
Yeah, so that would be like 2y squared. So I'm going to rewrite this and say that's the, I'm going to pull the 4 out first. And then I'm going to say this is 1 over the square root of 5 squared minus parentheses 2y. I'm squaring the 2y. And I hate putting the dy in the numerator. It should be up to the side, I think. That's right notation. All right, so we're getting close to this right here, that ideal form. So the a is missing in the top, right?
Mm-hmm.
I can just put a 5 in there, can't I? If I do what?
Divide by 5.
Divide by 5 out here. Okay, so that's cool. I'm missing one other little factor. Anybody tell me what else I'm missing? Literally a factor. Here's the way to think about it. If u was equal to 2y, what would du be?
2 dx.
2 dx, yeah. Or dy.
Or dy, yeah.
2 dy. So I don't have a 2 in here because there should be a chain rule, multiple of that 2 right there. So I could throw a 2 in here and then divide by a 2 out there. Would be one way to tweak it.
If we would have just pulled out a 2.
You could have just pulled out a 2 instead of the whole 4, right? That would lead, yeah, there's a lot of ways to play with the constants. Okay, so this is one way to kind of build it here. So the question is, what do I end up with? Well, I now put enough stuff in here to deal with a slight substitution and this formula here. So here's what I think the answer is based on this. I think the answer is I have a constant out here. Now 2 goes into 4, so my constant's really just 2/5 on the outside. And then otherwise, I have the arc sine of x over 5.
Would it be y over 5?
It's y, you are correct. We're using the variable y.
I mean, technically at the beginning you made it to an x, but then you kept going with the y.
Yeah.
Both wrong.
Be like 2 on the outside instead of 2/5.
You don't think there's a fifth on the outside?
Um,
There is going to be on the outside. 2/5. How can we check?
Take the antiderivative.
Take the, well, we took the antiderivative again to take the derivative to get back. Yeah, so we want to take the derivative of that. So I'm just going to try that, see if it works. Derivative with respect to x of 2/5 times the
Arc sine.
arc sine of x over 5. Who cares about the plus c, because the derivative of a constant is 0. All right, so the 2/5 hangs around. And then the derivative of the arc sine of x over 5 would be 5 over
square root.
Oh shit, I missed something. I have an error.
I think it's your x over.
Well, my x is a problem. Let's see. Here's the problem. What should that y be?
2.
It should be a 2y. Yeah, it should be a 2y. Let's go back here, up here. This should not be an x, but that should be a 2y. This is getting messy.
Yeah.
All right, so then let's see, down here, I'm going to get a 5 squared in the square root minus the numerator squared.
Wasn't that it?
And there's one more thing, the derivative of 2y is 2. Now, I've already,
And that's 5 times 2, so you'd have.
yeah, that's right. Yeah, so then the 5's divide out, 2 times 2 is 4. Is this what we started with?
yes. And
Yeah, that's what we started with there.
see 2/5.
Yeah, that's a hard one. All right, you guys want to do a similar one like this again, or do you want to take, are you going to do a similar one like this tomorrow? And you can ask about it tomorrow. Let's take a look in the last few minutes at the sample test. My guess is the hardest problem is the Riemann sum. So why don't we take a look at that problem, and we can look at others tomorrow. So problem number 30 here. So basically what I'm walking you through are the steps to try and use the definition of the definite integral. So first I'll state the definition of the definite integral, and then I'll go through a couple of these steps here. I won't have time to finish it today.
But the steps are not going to be on the test. It's going to be 5.
No, I'm going to actually walk you through these steps on the test.
Oh, great.
I'm not just going to say apply the definition. So this is what it means to apply the definition. The only extra step I have in here that's different than the definition is step B, where I say, hey, just give me an approximation of 4 with 4 rectangles. So the actual definition would be step C, D, E, F, and G would be applied to the definition. So first I'll state the definition. That's one of the questions on the sample test. So the definition of the definite integral So the definite integral is the integral from a to b of some function f of x dx. And the definition is to take the limit of a Riemann sum. Riemann sum, you have some index variable I that goes from 1 to n for n rectangles. And you would figure out what the special x values you're going to plug in are. Those are called our x stars. This gives you the height of the rectangle, and then you multiply by delta x, the width of each rectangle. And then the limit is as n goes to infinity. That's most of the definition. The only thing I'm missing here are what delta x equals. So delta x is equal to b minus a over n. And xi star is just some x value in the ith rectangle. Actually, I should say angel Riemann rectangle there. So if I asked you to state the definition of the definite integral, this is what you would say right there. I usually want f to be a continuous function, but there's a little wiggle room on that. I'm just going to skip that pronouncement. All right, so now we're just going to apply this. So we have to take the function we were given and the interval we were given and see what happens. So the function I gave here was f of x equals x squared plus 1, and the interval was from 0 to 2, I believe. 0 to 2, yeah. I said graph it on the interval from -1 to 3, so you can just, we're kind of zooming in on the section. 0, 2 is right in between there, exactly in the middle. So I'm going to jump right to the definition. To do the definition, I need to find delta x first. So delta x would just be the width of the interval, 2, divided by n subintervals. So 2 over n is my delta x. I'm going to recommend using right-hand endpoints. So if I go for right endpoints, my x of I is going to be starting at 0, add on delta x I times. So delta x cleans up kind of nice. It's just 2 over n, 2 times I. And I have enough information to build my sum now. So my, my right endpoint sum for n intervals is going to be the sum as I goes from 1 to n of the function evaluated at that x value. So that's the height. So I'm going to put a parentheses, and then another parentheses, 2 over n times I squared plus 1. That's plus 1, there we go. That's the height of each rectangle. Okay. Times the width, which is just 2 over n. So the next thing we do, so this is like part C, I think, on that. Actually, this was part C right here, and I think here I'm in part B, maybe. So that would for that problem. So next thing I want to try to do is clean this up right here. Now, technically, n is a constant here. It's fixed at 100 or 4 or whatever. So the 2 over n can be pulled out of this. So now I'm trying to clean this up. So I have 2 over n times the sum, I goes from 1 to n, of 2 over n times I squared plus 1.
Notice how that cleans it up a whole lot, though.
Well, we can clean up a lot more. What's that?
We can separate the plus 1.
Yeah, we can separate on the sum there. So I'm going to keep the 2 over n out here. But now I'm going to have the sum as I goes from 1 to n of the 2 over ni squared plus the sum of 1.
And that would just be n, right?
Yeah, so this thing right here is just going to be n. Right? Got time?
Yeah.
Okay, so real quick, the next part. This 2 over n squared is just a constant. So it's going to come out. And then I just have the sum of the I squares, which I gave you a formula for.
Oh, and then you can just.
Yeah. So if I put all this together, I get 2 over n times 2 over n squared times the sum of the I squareds. I'll finish this tomorrow, but let me write this down quick. I squared is n plus 1, 2n plus 1 over 6.
Will you give us this one?
Yeah, I'll give you those formulas on the test. n plus 1, 2n plus 1 over 6 plus n. Right, so I can break all of that down. So the next thing we have to do is try and clean this up and see if we can take the limit as n goes to infinity. We'll pick up with that tomorrow.
What's on the non-calculated section?
This is on the calculator section.
Okay.
Yeah. And this is one reason I said, let's do this for n equals 4 first,